Hello everyone, we are Team 22015 and we are going to be talking about our senior design project called the Forward Motion Blur Correction System, which we'll be referring to as the FMBC. This project was conducted under the sponsorship of Arete, and we'll now go ahead and introduce the team.
Hi, my name's Sarina Grijalva and I'm studying optical engineering and I'm also the procurement lead.
Hi, I'm Jacob Eberhard and I'm studying ECE and I am the team lead.
Hi, I'm Diana and I'm studying engineering management.
Hi, I'm James and I am studying systems engineering.
Hi, I'm David and I'm studying mechanical engineering. Airborne imaging is not a new phenomenon, and therefore the solution for correcting for that induced motion blur has previously been solved in the form of a camera gimbal which follows the ground object as the aircraft is in flight. Such a solution became inefficient for Arete clients since the cost of these camera gimbals are extremely high.
Our solution to this problem is to eliminate the gimbal completely and base our design off of the concept of line of sight stabilization. This means that instead of moving the whole camera system on a gimbal, we will just be moving the focal plane of the camera. This concept will allow stationary objects to not appear blurry on the detector of the camera. A more conceptual way to think about this is if you were driving in a car and look out the window, the image you see will be blurred. When you snap your head back and forth, you will get a momentary image of clarity on what you're looking at.
The phenomenon behind this principle can be further explained through fundamental optics. We know that when an incident ray of light passes through the center of the lens, it will continue in the same direction that it entered at. But if the incident ray was instead headed for the rear focal point of the lens, which is usually the case, it would refract through the optic lens and have a different optical path. So in order to compensate for the moving vehicle, as Jacob previously mentioned, the focal plane of the camera has to move at the same rate but in the opposite direction so that it cancels out any otherwise induced blur. This also keeps the axes aligned so that the ray is passing through the center of the lens and is imaged onto the detector.
One huge consideration with this project was the feasibility of testing. Since the project was initially geared towards aerial use, specifically on jets, we ran into the problem of not being able to test our FMBC system since we don't have access to that resource. As a result, we scaled our project down to a simple ground vehicle scenario, thus splitting our design concept into a theoretical plan of action and then a practical plan of action, which enabled us to conduct our tests.
This is what our system architecture looks like with the major subsystems for the FMBC. The four main components are the lens subsystem, the mechanical, the motion, and the software subsystem.
This is our system block diagram, which shows another visual to our subsystems as well as what we initially decided was our critical design component. Since the whole idea behind the motion blur correction is based on the movement of the focal plane, we considered this our most critical component and made sure that we calculated the correct speed that the stage would need to move, and also made sure that we found a stage that could move fast enough in general.
Brings us to our design approach, which is that we connect the camera to the stage using a fixture that we designed and 3D printed. The lens is then placed in front of the camera so that the target we are looking at can be imaged through the lens to the focal plane of the camera. This design concept resulted from a lot of analysis and trade studies to come up with the optimal solution. These are some of what the trade studies look like.
This was a trade study we conducted when choosing our camera based off specifications such as pixel size, Nyquist frequency, and the type of detector. Due to shortages of parts, we ended up borrowing a camera from Arete, but it had similar specs. For the lens trade study, we focused specifically on the field of view specs as well as the IFOV considerations. This diagram shows the relationship between resolution in image space versus resolution in object space.
This analysis shows calculations of the speed the stage is required to move based on the requirements of this project. This analysis determined the speed that the vehicle is required to move based off of various distances to prepare for final testing. Through these analyses, we were able to determine what qualifications our stage needed to accomplish our goals, and purchase the stage accordingly. This linear stage will work through the snapback principle and will allow for the stage to accelerate to the desired speed to correct for motion blur.
These are some of our final acceptance test plans for testing related to the stage as well as the picture quality.
For the final test day, there were some considerations we had to build outside of our physical testing system. This specifies the ground vehicle we used, which was an electric scooter with a speedometer, and the platform the FMB system sits on, which was an optical breadboard that sits on the scooter via wooden board. This also specifies the target we are looking, which is a high contrast black and white board, and the testing locations, which were the U of A campus and Marana Field. Other parts that were included that were outside of the system design are a 3D printed camera to stage interface connector, the FMB system encasement, a piano dolly, and wooden platform with foam underneath to absorb noise.
To prepare for test day, we followed steps to build up the platform that the FMBC system will be sitting on. which is this dolly, piano dolly, that's securely fastened to the scooter, and then we have this platform here with foam to reduce noise, and then that's our FMB system with the enclosed encasement, and then when it's opened. We set our target at 66 meters away, and then we ran our code where the camera first initializes by homing and then being put in place, and then this video now shows the camera in motion.
The modulation transfer function helps determine the contrast and resolution in an image. MTF is calculated by measuring the line pairs per millimeter. On the left is a graph of good MTF plot for an image, and on the right is a graph of a bad MTF plot. In order to use data from the MTF plot, we looked at the scaled values of the Nyquist frequency, which is the highest frequency resolvable. These following photos are examples of the process of the stage moving. The MTF plots look better as the photo increases in image quality. This graph shows the MTF values of 23 photos at Nyquist frequency. The graph goes through 2 loops of the test where we desired to have 2 photos that corrected image blur to within 10% of the MTF values of a still photo taken. Photo 18's MTF value is within 10% of the range of the still photo. This graph shows the MTF values for the photos at 50% Nyquist frequency. We now see the 2 peaks that we expected to see previously. Photo 18 does not fit within the 10% range, but is within 16%. This graph shows the MTF values for the photos at 25% Nyquist frequency. We still see 2 peaks, but now the values are within the range of the still photo or are greater than the range. These graphs help us understand that the FMBC system does correct for motion blur within 10% of a quality photo. We discovered that even with still photos, the MTF values at Nyquist frequency can have a large range, and the lower the frequency, the wider the difference is between good or bad quality photos. The MTF value decreases as the frequency increases. With good quality photos, we are able to see good contrast and resolution in the curve of the MTF, while in a bad quality photo, the value drops fast, and there are many peaks and troughs throughout the graph.
Some of the improvements we could make is finding a different way to stabilize the FMBC system because we still encountered some noise. Another one would be to improve the accuracy of the vehicle, and then lastly find a way to automate the calculator of the MTF of the photos so that we could get our graphs and results much faster.
We are planning on delivering 5 items to Arete at the end of the project. First, we will be delivering a systems requirements document, technical data package, and our engineering notebook. In addition, we will also physically be delivering the entire FMBC system. The final item we will be delivering is our final report, which includes our test results, all relevant documents, and potential next steps for the project.
And now we'd like to give acknowledgements and thanks to our mentors at Arete, Chris Ryerson, Kyle Hawkins, and Patrick Baker, and the U of A faculty, Heather Hiltzendager, Scott Wright, and Debbie Claggett.
Thanks for listening.